Okay, it's time to finish our Chapter 6 lessons. So I want to start with where we ended after the activity last class and where we are up to with this binomial distribution. We're still talking about the binomial distribution for the first half of this video. So remember, a binomial distribution is a discrete random variable. It is binary, success and failure. Each trial is independent, fixed number of trials, and the fixed probability of a success. What we gathered last class through the activity was that if it is a binomial setting, we can find the expected value and the standard deviation using abbreviated formulas. We knew we found the expected value and the standard deviation in section 1 of this chapter for any discrete random variable, but it is much simplified for a binomial distribution because the probability is fixed, because the probability does not change. So we have our expected value, n times p, and our standard deviation, square root of n times p times 1 minus p. Now, the binomial distributions are important in statistics when we wish to make inferences about the proportion p of successes in a population. Almost all real-world sampling, such as taking an SRS from the population of interest, is done without replacement. However, sampling without replacement leads to a violation of the independence condition. Think about this. Whenever we did our SRSs in section 5 with our random digit table, we wouldn't repeat. So when we don't repeat, does that technically violate the independence condition? Yeah, it technically does. But when the population is much larger than the sample, a count of successes in an SRS of size n has approximately the binomial distribution with n equal to the sample size and p equal to the proportion of successes. So we have this new condition. We have this condition for using, when sampling, we have to make sure the population's at least 10 times larger than the sample. Because if you're sampling without replacement, which is almost any time there's a sample, we want to make sure the population's at least 10 times larger than the sample, because then we can assume independence. So this 10% condition is so we can assume independence when sampling. So it's when we can't assume independence by just saying it straight up, we have to just say, okay, if the population is at least 10 times larger than the sample, we are safe to assume independence. So when taking an SRS of size n from population capital N, we can use a binomial distribution. So basically what it's saying is we can assume the independence part of bins is met if the population is 10 times larger than the sample. It's part of establishing the I in BINS. You're gonna need it. And now, I told you a few times it was very important to realize the binomial distribution is discrete. Well, as we get larger, so as n gets larger, as our number of trials increases, the binomial distribution is replaced, because to try and use a discrete random variable with many, many samples doesn't make sense. So as n gets larger, something interesting happens to the shape of a binomial distribution. The figures below show a binomial distribution as it gets larger, meaning what's it? N, the number of trials. So we have these number of trials with outcomes, histogram here with 10 trials, p of 0.8, 20 trials, p of 0.8, 50 trials, p of 0.8. What distribution do you see this approaching? Well, it told you at the top, the normal approximation. So essentially, the binomial distribution is good and useful when the sample size is small. As the sample size gets big, the normal approximation is the correct way to solve these problems. So I want to just put this very important note. As sample size gets big and you are okay to use the normal distribution, you have to use the normal distribution. You can't say, oh, well, I chose to still use the binomial even though I could have used normal. That is not going to be correct, so pay very close attention. So, suppose that x is a binomial distribution with n trial successes, fixed probability p. When n is large, we will talk about what large means right there. When n is large, the distribution of x becomes normal, okay, approximately normal. And our mu sub x, mean of the sampling distribution, will be n times p, which is the mean of a binomial. And the standard deviation, sigma sub x of our random variable. If we square root of n times p, that's 1 minus p. Essentially, you are going to use normal calculations, but use the mean for the binomial and use the mean for the standard deviation for the binomial. Now, here's the rule of thumb. This is the when do I use normal approximation. Okay? What I'm about to say means you are replacing binomial PDF and binomial CDF with normal calculations if n times p is greater than or equal to 10 and n times 1 minus p is greater than or equal to 10. If both of these conditions are true, that is the expected number of successes and failures are both at least 10, you switch and use normal calculations. Let me show you how it works. So, sample surveys show that fewer people enjoy shopping than in the past. A survey asked a nationwide random sample of 2,500 adults if they agree or disagree that I like buying new clothes, but shopping is often frustrating and time-consuming. The population that the poll wants to draw a conclusion about is U.S. residents age 18 and over. Here's our problem. Suppose that exactly 60% of all U.S. residents would say agree if asked the same question. Let x equal the number in the sample who agree. Okay? Show that x is approximately binomial. So basically, with the information we have here, let's show B-I-N-S. First, is it binary? It's absolutely binary because they either agree or disagree. Two options. Independent. This was surveys. This was sampling. So they are not technically independent. But if we can show the population's at least 10 times larger than the sample, we can assume independence. Well, there's a sample of 2,500 adults, and the population is all U.S. residents 18 and over. Yes, it is safe to assume the population is at least 10 times larger than 2,500 because all U.S. residents is way higher than 10 times 2,500. It's a safe assumption. N, fixed sample size. Suppose that exactly U.S. residents would say, yeah, fixed sample size, 2,500. Right there, 2,500. And then fixed probability, yes, 60%. So here is our BINS written out. Take a look. Success is agree, failure don't agree. Independent, this is what I was just talking about. The trials are not independent, but the 10% condition is met, meaning there are, an easier way to write this is there is at least 10 times more than 25 U.S. residents, 18 and over, meaning there's at least 10 times the sample size. 2,500 fixed trials, there is the same probability of selecting an adult who agrees, so fixed probability of 0.6. So the number in our sample who agree that shopping is frustrating is a random variable x. It is binomial, 2,500 and 0.6. Letter B. Check the condition for using the normal approximation hold. So you have to know to check this. If the sample size is very small, that tells you it's probably going to be answered with binomial. As the sample size gets bigger, that is when you have to think this might be normal. So what do you have to check? Well, we have to check n times p, 2,500 times 0.6, that's 1,500. N times 1 minus p, 2,500 times 0.4, that's 1,000. They are both at least 10, so we are safe to use the normal approximation. You are more than just safe, you are supposed to use the normal approximation. So yes, is it a binomial random variable? Absolutely. But are we going to use a normal distribution, meaning a continuous distribution, to approximate a discrete random variable? We are. Why? Because it's much easier to use normal calculations in terms of the generic statistics world. Whenever something can be normal, you try. So use a normal distribution to estimate the probability that, so 15, 20 or more. What does that mean to us in a normal distribution? It means lower bound 15, 20. Upper bound infinity, meaning huge number, right? We always put in like 100,000, 10,000, 20,000 for a upper bound. What's the mean? Well, this is why it's important that it's binomial. The mean, we already just found it. We found that n times p was 1,500. There's the mean. What's the standard deviation, you ask? Because we need that. Remember our formula. Square root of n times p times 1 minus p. So you just need to, you just need to find those. N times p is 1,500. Sigma, square root of n times p times 1 minus p is 24.49. So now think about what you have. You have a lower bound. You don't have an upper bound, so you put a huge number. You have a mean. You have a standard deviation. That's all you need to do a proper, normal CDF. So yeah, do you need this picture? No, but it's great visual. We needed to find the mean. We needed to find the standard deviation. Once you have them, come to the bottom of the slide with me. Norm CDF, labeled lower bound, labeled upper bound, label the mean, label the standard deviation, and you get 20.71. Please remember, don't just say, oh, 20.71. No, answer the question. What is the answer to the question? There is about a 21% chance of getting a sample with 1,500 or 20 or more that agree with the statement. That's what you found. You found the probability, if 60% would say yes, the probability of getting a sample of 2,500 people and having 1,520 of them or more say yes is 21% chance. We used a normal approximation for binomial. You're going to have to use this anytime it's applicable. And when is it applicable? When this large counts condition are both greater than 10. Secret here, if the sample size starts to get bigger, look for this. If the sample size is really small, then it's going to be binomial PDF, binomial CDF. That's it for binomial. There is one more distribution in section 3 that you can't go home without seeing. It is very simple. It is the geometric setting. In a binomial setting, the number of trials is fixed, right? BIN, fixed number of trials, n. Geometric setting is to use to answer one and only one type of question only. In other situations, the goal is to repeat a chance behavior until your first success occurs. A geometric setting arises when we perform independent trials of the same process and record the number of trials it takes to get one success. On each trial, we still have a fixed probability. Yes, just like the time we had this slide, if you think about one geometric random variable, it would be, if we define a random variable y to be the number of trials needed to get the first success, y is the geometric random variable. The distribution of all y's is a geometric distribution. The probability distribution of y is a geometric distribution with parameter p. The probability of success on any trial, the possible values of y. So this is the random variable is just one singular. A distribution means to look at them all. That's how this class works. This more vocab than actual necessity here. But look, like a binomial random variable, it is important to be able to distinguish situation in which geometric does or does not apply. Here we go. The lucky day game. The random variable of interest in this game, this is from your reading, is y equals the number of guesses it takes to correctly match the lucky day. What is the probability that the first student guesses correctly, the second, third, fourth, the probability that k student guesses correctly? So here's how this game works. A teacher picks one day of the week and says that will be the lucky day. And they pick a person, they pick a student, and they say, what do you think the lucky day is? And the student says Monday. If they're right, then that is it. It's over because the first success happened. If they're wrong, and here's why it is independent trials. If they're wrong, the teacher would re-pick a different day of the week to be the lucky day. It could be the same day, or they could pick a different one. And then they would pick a new student, and that student would say, I say Tuesday. And the teacher says, no, still no success, go to the next one. The game continues until a first success occurs. So what are we doing first? Think about it. The probability that the first person picks the lucky day is 1 out of 7. There were 7 days, they picked one of them. They had a 1 out of 7 chance. Here's how this probability, it's a very easy distribution to make because there's only one success. Everything before it is a failure. So the probability the second person picks the lucky day means failure first, success second. A failure means the first kid picked one of the 6 out of 7 days that wasn't the lucky day. Then the second kid picked the lucky day. Geometric distribution is failure, 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 and then one success. So it's a very easy distribution to make. It is the probability of a failure raised to all of the trials except one times one success. Because a geometric probability question, way different than binomial, it is trials until the first success. So the formula is how many failures, the probability of a failure raised to how many times one success. A geometric distribution, unlike a binomial, is always right skewed because the highest probability, look, the highest probability, 1/7, is that the first person gets it right. Because once you do failure times success, failure, failure, success, the probabilities can only get smaller because you keep multiplying by something less than 1. So the geometric distribution is always right skewed. So you actually never can show the end of it because technically it is a continuous distribution because it always technically could be the person never gets it. It's possible. It's not, the probability is near 0, but the table for a geometric distribution continues. What's the shape of this? Heavy right skew. What's the center of this? Well, the center of this is the expected value. The center is mu of y and it's 7. We'd expect it to take 7 guesses to get the first success. What's the spread of this? The standard deviation is 6.48. In the class played the lucky game, here's the definition of standard deviation. Many, many repetitions, the typical variation. So look, if the class played the lucky day game many, many times, the number of homework problems that the students would receive, that's what it was about. If they picked the lucky day, it was about how many homework problems they get for the night. The number of homework problems the students would receive would differ from 7, which is the expected value, by about 6.48. Here's the formula for variance of a geometric distribution. It's 1 minus p divided by p squared. So the standard deviation is the square root of that. So, moral of the story is we get our formulas right here. We have our standard deviation, which is square root of 1 minus p over p squared, and we have our expected value, which is 1 over p. 1 over p is our expected value for geometric. These two things, we don't really use them very much. What do we use geometric for? We use geometric in our calculators. So I'm going to show you how geometric works in your calculator, and that indeed will be the last thing we cover in this chapter. So stick with me. So where is it? Second vars gives you your distributions. We've done normal today. We've done binomial last class. And our last two are geometric CDF and PDF. They are the same as binomial PDF and CDF in that PDF is for the exact trial number of success. What do I mean by that? We had a 1/7 probability of a success in the lucky day game. If I put here 3, what does that mean? For a PDF function, it means on the exact third student, exactly 3 students, you will get the success. 0.104. So what does this mean? It means fail times success. Fail times success. 0.104. If you look here, there it is. 0.105, 0.104. That was our exact thing. That's exactly what we had before. 0.1049, so 0.105, just like the slideshow showed. Geometric CDF does cumulative, meaning does it happen? Let me do it for you. Geometric CDF, which will always be higher, so 1/7, x value 3. So same numbers I'm putting in. And what is that? How to go from 10 to 37? I'll tell you what geometric CDF is. It's cumulative with ORs, meaning it means will the lucky day, will the first success be picked on the first student or second student or third student? So this is doing 3 PDFs at once. It's doing success on the first, success on the second, success on the third, and adding them up. It's 37. Let's go back to the slideshow. Look, 1/7 plus 12 plus 10, that is the 37, meaning 1 or 2 or 3. It's not saying 1 success or 2 successes or 3 successes. No, no, no. It's saying the first success, meaning the game ends. Does the game end on the first student or the second student, or is the first success on the third student? And it's adding those probabilities together. That is geometric. It is for measuring the first success. So today we turned binomial PDF CDF into normal CDF if you have large counts. And then we did a totally separate thing on the geometric distribution. That is it for chapter 6. Your slides are all done. No more lectures.